Geometry, and this is Lab 2, Motion of a Falling Object. In this lab, we were to observe the position of an object falling at a constant velocity with respect to time. We used two glowstream models to predict the movement of an object. We used one that just accounted for the force of gravity, and we used another model that accounted for the force of gravity and the drag force acting upon the object. Then we did an actual experiment where we dropped an object and we measured its movement in tracker software. I used a cardboard box, and using its dimensions, I created the two predictive models. Here's the first predictive model. Here is the model just accounting for the force of gravity with the drag coefficient equal to 0, so that there would be gravity only. Here is the ball falling just in the negative y direction with no drag force moving in the opposite direction. Here is the model accounting for B. I derived B to be 0.755 kilograms per meters, and I'll explain how I did that in the main idea section of the presentation. And here you can see the drag force as the cyan arrow and the force of gravity as the orange arrow, where they move in an equal and opposite direction. Here's my live experiment. Dropping a cardboard box and measuring the distance, the change in y, in intervals of 0.033 seconds. So here is the two predictive models versus the live experiment. The no drag model is the red data points. The drag model is the blue data points, and the live experiment is the purple data points. As you can see, there was extremely strong correlation during the first near the beginning of the experiment between the no drag and drag model, but slightly more disparity happened as time increased. The highest disparity, though, is between the live experiment data and the drag and the no drag models. It seems that there are other unaccounted forces acting upon the actual box in the live experiment that caused it to fall not as quickly as either the no drag or the drag model. The no drag model fell the quickest. This makes sense, as there would be no drag force acting upon it. There'd be no drag force acting upon it to slow it down. And so overall, it seems that there are other forces acting upon the box which cause it, besides drag force, that cause it to fall not as quickly as either computational models predicted. The main ideas used in this experiment were Newton's second law and the equation of the drag force. The object moving at constant velocity will have a drag force acting in an equal and opposite direction, causing F net to be 0. And this can be used to solve for the drag coefficient as shown below. The final velocity can be found using this kinematic equation. So the second model, the model with a non-zero drag coefficient, predicts a terminal velocity, since negative mg plus b times v squared is equal to F net is equal to 0, cannot have b equals to 0, as that would cause it would be impossible for F net to be 0 unless the mass was 0 or g was 0, and that is impossible in this experiment. If it was thrown downward initially, the terminal velocity will be different, since there will be a different final velocity. As shown in this kinematic equation, there would be a non-zero initial velocity, and that would change the drag coefficient. To conclude, there are more forces acting on the falling box than the drag force, which causes it to not be perfectly predicted by the second model, which accounts for drag force. It seems that there are unknown forces acting upon the box, which cause it to fall slower than predicted. And this concludes my Lab 2. Thank you.